Hello students, welcome to HashLearn. I am Sri Harsha, your physics mentor, and we are dealing with the optics in the second year, okay? And we have completed the ray optics and the optical instruments. Now we are going to the second part of the optics, which is called as wave optics. So the chapter name is wave optics, and we are gonna study the certain properties of light which shows the behavior of wave nature. So as the topic I told you, it is wave nature, and in that we are dealing with the concept called as interference. So before we have the regular drill, in the previous class we dealt with the multi-concept problems. We solved few problems on the ray optics, and we solved certain very interesting problems also. We also solved the match the following type questions also. So in that we have the most important CVP question over here. The focal length of the objective and the eyepiece of a telescope are 25 and 2.5 centimeter. The hi Yogesh, very good evening, welcome on board. The telescope is focused on an object of 1.5 meter from the objective, and the final image is formed at 25 centimeter. We had to calculate the length of the telescope. So from the lens equation we found out the image distance. And hi Peru, very good evening, welcome on board. And with that we also calculated the this is through the objective, this is the image distance through the objective, and this is through the eyepiece, right? So we calculated, and we know that the length of the tube, or the focal length, or the length of the telescope is given by VO plus UE. So from this we get the focal length, the length of the telescope as 32 centimeters. So which means the correct option is option C. So now we have the next important, the goal of the today's class is interference and the numerical problems based on that. So we are going to start from the core. The chapter name is wave optics. So first, before we start with the wave optics, we have to know what a wave is. We are very familiar with this word called as wave, or it is also called as the ripples. I mean, you can relate it to the ripples on water. So wave is something which is, okay, let us take a simple example. If I have to pass an object to you, I have to pass the entire mass to you. That is the ray optics, what we discussed. But over here in the wave optics, when you create a disturbance in the medium, that disturbance transmits energy from one point to another. The disturbance in the medium transmits the energy from one point to another medium, and that is called as the wave. A disturbance in the medium which transmits energy from one point to another is called as the wave. The wave are of two types. One is called as the transverse wave, and the other one is called as the longitudinal wave. So in the transverse wave, if this is the propagation of light, the particles vibrate perpendicularly to each other, so it will have a crest and a trough. Whereas if this is the direction of light, the particle vibrates like this in the longitudinal wave, which forms compression and rarefaction. Here you will have it as crest and trough. The maximum displacement is called as the amplitude, which we have learnt in the alternating current chapter. So the particles execute SHM over the mean position, and the energy is transformed. If they are perpendicular to each other, then they are called as transverse. If they are parallel to each other, they are called as longitudinal waves. So we know what is the displacement and all those things. So light is a transverse non-mechanical wave. So we can consider the light as transverse non-mechanical wave, which means it can even transport in the vacuum. So light is a transverse non-mechanical wave. It does not require any material medium to propagate. So now, before we start the main concept, we have to know the first important concept is called as Huygens principle. What actually is this Huygens principle? Now, if you take a source, so this is a source S, which is a point source, which emits the light in all the directions, So this is the direction in which the light rays are emitted. And here you have the particles which are vibrating perpendicular to the propagation of light. In that, at a certain time t, I choose all the particles which are vibrating along the same phase, which means these 8 particles as shown in the figure, they are oscillating simultaneously. They are going up together and coming down together. You take those particles and mark them. So if you take those particles and mark them, and if you join them, if you join all these points, they give rise to a geometrical shape, and this is called as wave front. It is called as wave front. What actually the wave front is? In simple language, the front of the wave is called as the wave front. So it depends on 2 things, the type of source and the distance between the source and the observer. So if you have a point source, it will give rise to spherical wave front. It will give rise to the spherical wave front, which is the previous example what we discussed. If you have a linear source, then it will give rise to cylindrical wave front. Here the distance between the observer and the source is small. If the distance between the observer and the source is very, very large, then it will give rise to plane wave front irrespective of the shape of the source. Irrespective of the shape of the source, it will give rise to a plane wave front if they are very far apart at infinite separation. So wavefront is the locus of the particles which are vibrating in the same phase. So I took an example. So if you have a point source, you have the rays of light coming outside in all the direction. You have particular particles which are vibrating along the same phase. You join them, that gives rise to the locus or the path traced by the particles, and that is called as wavefront. Now coming to Huygens wave principle, so you should always remember 2 things. So Huygens wave principle. So if you take, again I take a point source, it is easy to understand. So you have 4 or 8 rays which are traveling by the source, and you take the locus of the particles which are vibrating. Rakesh Kumar Nepak, thank you so much. And if you take the locus of this particles, this will give rise to a circular path. What is according to the Huygens wave principle is each particle on the ray will act as a disturbance for the neighboring particle. Each particle, so this particle P1 will disturb the neighboring particles, so it will have one more smaller circle around it. So this is called as wavelet. So this is called as wavelet, and this is called as wave front. So according to the Huygens wave principle, it is, if you have to consider this or analogy for this in the simple languages, it is like passing the message. The source will disturb the surrounding medium, and each disturbance will disturb surrounding around it. So this is called as primary wavefront. So this is called as primary wavefront, and this is called as secondary wavelet. And this is called as secondary wavelet. So similarly, if you take the particles of the secondary wavelet and when you join them, this gives rise to secondary wavefront. This will give rise to secondary wavefront. So the Huygens wave principle can be told in 2 points. The first point is each particle on the primary wavefront is a source of disturbance for the secondary wavefront. Each particle on the primary wavefront is a source of disturbance on the secondary wavelet or wavefront. When you join the outline of the secondary wavelets, that gives rise to the secondary wavefront. So one particle disturbs the other and you draw the outline, that will give rise to the secondary wavefront. Now you might have one more question in your mind. Why can't we take the backward direction into the account? Why can't I join this? Why can't I join this? Why can't I join this? We do not take the energy in the backward direction for one particular reason, is that this source of light is continuously on and is emitting radiation continuously, so the energy cannot travel backward. It cannot travel energy backward. So it is also called as a factor which is called as obligity factor. So according to this factor, the satisfying condition should be 1k equals 1 plus cos theta for backward direction. For backward direction, theta is equal to 180 degrees or cos theta is equal to -1. So k becomes 0, which means there is no energy transformation in the backward. So energy cannot go in the backward direction. So this is Huygens principle, which is very, very, very important in solving to understand the concept, students. Now using the Huygens principle, we will take a very small explanation which can be explained for the reflection or refraction, and using which you can, if I'll be doing only reflection for you, but refraction you can do it simultaneously using the Huygens wave principle. Okay, so that is the first point over here. So now the Huygens wave principle can be applied to the reflection as well as for the refraction. Now let us assume you have a surface or a mirror. Let us assume you have a mirror or a reflecting surface. This is the surface which is reflecting, and you have a plane wavefront which is incident. You have a plane wavefront which is incident, and you assume this to be the normal, and this is making an angle of incidence I. Now let us assume this angle is equal to, the position is AC, and you assume this is the normal. Now if I draw a perpendicular from the point A, it reaches the this is your first first ray, and this is the second ray. So AB is the, so now the second ray is traveling an excess of distance. So it is something like when you take a two oblique parallel lines, they strike the surface at two different times. So it is traveling an extra distance which is equal to x. So that x will be equal to c into t, because this is from the formula speed equals distance by time, or distance is speed into time. In this mean time t, the ray 1 would have emitted or would have sent a reflected ray backward. So this is the reflected ray, and you draw another perpendicular. So this distance is x dash, but it is x dash will be equal to x because the speed is also same and the time is also same, and this angle is angle of refraction. So you're getting the point. By the time the ray 2 reaches the surface, the ray would have sent a reflected ray, because this is traveling an extra distance. So now if you take the triangle, this is your ABC, I'll call this as D and B. So in the triangle ADC, and triangle ABC. I'm taking two triangles ADC and ABC. So you're taking the two triangles ADC and ABC. So here AC is equal to same, and I can say AB is equal to CD because X is equal to X dash, which is equal to C into T. And from this so which means, and AC is a common side for both the triangles. So common side for both the triangles, so which means these triangles are congruent. So for the congruent triangles, the angles will be same, so which means angle of incidence is equal to angle of reflection. So this is also called as the proof of the law of reflection using Huygens wave principle. So this is what has to be understood, students. Okay, now you can take this as your ray 1 and ray 2. If I keep them parallel with each other and the surface is somewhere over here, so this has to travel an extra distance to collide to the surface. In that meantime, this ray would have been reflected back. So by the time this reaches, this ray would have been reflected back. So that perpendicular distance, when you join them, that gives the extra distance traveled. So I hope with this you will have a clear understanding of the concept, what is actually happening in the reflection. And this can also be applied to the refraction, students, where you can, using this, you can also prove the Snell's law of refraction, but I leave that to your as a homework. So because we have to go with the further concepts, so I'll leave that as an homework. You can work on that, so using which it will become very easy for you to understand refraction and to also prove that sin I by sin R is equal to constant. So now we are going into the main concept, which is called as the interference of light. So what is actually the interference of light, or what is this? To understand this, we will start with a beautiful example. So let us assume for the fun's sake, you can take it as just for fun. I'm taking this as an example. Now imagine you are reading for your test or an examination where you're trying to concentrate. So let us say your concentration is the maximum possible level, and suddenly you get a message or a call saying that in wave optics a question on interference is confirmed. Before writing the test, it is almost something you know the question paper, and then what happens, your concentration increases. But if I say you're reading interference and I say that this question is not going to come for your exam, then your concentration decreases. What actually is happening? An external factor is trying to increase your energy. An external factor is trying to increase our energy, and similar things happen over here. Now let us assume I take one wave. So this is the crest and the trough, and you have another wave which is moving in the same direction, but the condition is the crest and the crest are coinciding. When you add them, the energy increases by increasing the amplitude. So this is called as coherent addition. Or if you take one wave, this is the another wave, and you have the another wave which is exactly ulta of these two, and this will give rise to a plane wave, and this is called as incoherent addition. So here the brightness increases, energy increases, amplitude increases. But over here the brightness decreases, amplitude decreases, and the energy will also decrease. So the interference is classified into two types, the crest and crest, or when the two phases of the same phases meet each other, it is called as coherent. When they don't, when the opposite phases coincide, it is called as incoherent. Right, so now we'll go to the mathematical treatment of the interference. So mathematical treatment. So we know the very basics of the equation, the wave equation, mathematical treatment. So this is very, very important to understand the concept. So let us say you have y1 is the first equation, which is given by a sine omega t, and y2 is the another equation, which is given by a sine omega t plus phi. Y1 is the position of the particle 1, a and b are the amplitudes, omega t are the angular frequency and time, and phi is the phase difference. Now from the addition you will have it as y equals y1 plus y2. So you will have it as y equals a sine omega t plus b sine omega t plus phi. And if you equate this, you will have it as a sine omega t plus, you will have it as b times sine a cos b plus cos a sine b. Sorry, cos a and sine b. So this is the basic geometrical formula which we know, and from this you can write this as y equals a plus b cos phi sine omega t plus b sine phi cos omega t is the equation. In the simplest form it can be written, and I'll make a small assumption over here saying that let a plus b cos phi be equal to r times cos theta, and b sine phi is represented as r times sine theta. So from this, if you write this equation, you will have it as r times sine omega t cos phi, sorry, cos theta plus cos omega t sine theta. This is again of the form sine a cos b plus cos a sine b, which can be written as sine omega t plus theta, which can be compared to y1, where r is the resultant amplitude. R is the resultant amplitude. We will go this in detail. R is the resultant amplitude and theta is the phase difference of resultant wave. Resultant wave with respect to y1. So theta is the phase difference of the resultant wave with respect to y1. This point has to be in your mind all the time. You can never go, it is always with respect to y1. So now we will discuss about the amplitude. So you have to remember these two equations. I'll call this as equation A and equation B. So from the equation A, you will have it as a plus b cos phi is equal to r times sine theta, and b sine phi is equal to r times cos theta. Sorry, this is r times cos theta and this is r times sine theta. So if you square and add them, you will have it as r square equals a plus b cos phi square plus b square sine square phi, or this is equal to a square plus b square cos square phi plus 2ab cos phi plus b square sine square phi. Again, sine square theta plus cos square theta is equal to 1. So you will have it as a square plus b square plus 2ab cos phi. Isn't this equation very familiar to us? We have been dealing with this in the first class, and this is similar to your parallelogram law of vector addition. And the tan phi, if you divide these two, you'll have it as tan theta equals b times sine phi divided by a plus b cos phi, which gives the phase difference. So this gives the phase difference and this gives the resultant amplitude. So now using these two equations, we are gonna derive the conditions for coherent and incoherent, or wherever you have a dark band or a bright band. So when you have the crest and crest meeting, it is called as constructive interference. This is the equation. So now it is classified into two types. The first one is constructive. So in constructive, this gives rise to bright band, or in simple language, the crest and the crest will meet. So in that condition, the cos phi is equal to +1. In that condition, you'll have it as r square equals a plus b the whole square, or r is equal to a plus b when cos phi is equal to +1. and the condition for that is 5 equals 2 times n pi. The even multiples of pi will give rise to constructive interference, even multiples of 5, and from the integral multiple of 2 pi it is giving you the constructive interference. So this is the phase difference. Now coming to the path difference. So path difference, delta is equal to lambda by 2 pi into phase difference. So phase difference delta phi. So if you substitute this, you will have it as delta equals lambda by 2 pi into 2n pi. So pi gets cancelled. So delta equals n lambda is the condition for constructive interference giving rise to a bright band. So constructive interference is giving rise to a bright band. So this is the important concept. Now coming to the second one is for destructive interference. For destructive interference, it will give rise to a dark band. So here you have the equation r square equals a square plus b square plus 2ab cos phi. The minimum value possible is cos phi is equal to -1. Then you will have it as r equals a minus b, and the condition is 2n plus 1 times pi, where n is equal to 0, 1, 2, 3, or you can also use the equation 2 times n minus 1 into pi, but n value is 1, 2, 3. So these two conditions you can remember any one. And again you will have delta equals lambda by 2 pi into delta phi. So lambda by 2 pi into 2n plus 1 times pi, which gets cancelled. So delta equals 2n plus 1 times lambda by 2. So this is the condition for destructive interference. When you plot the curve of energy versus distance, when you plot the curve of energy versus distance for the interference, this will be the pattern. So this will be the pattern. Or if you plot the curve, this is a bright band, dark band. So this will be the interference pattern. One is bright and the other one is dark. So one is bright and the other one is dark. Each will be of same thickness. Remember this. Each band will have the same thickness, and each bright band will have the same intensity. Each dark band will also have the same intensity. So this is interference, which can be, from the derivation we can define it as the modification in the intensity of light. Modification in the intensity of light due to the redistribution. Due to the redistribution of the light energy. Redistribution of the light energy in the region of superposition. The modification of energy of light due to the superposition of the light energy. So that was the interference. Now we have a small experiment based on that, and it is called as Young's double slit experiment. So Young's double slit experiment, it is very famously known as YDSE. So now what happens over here is you have a source of light and you have a small slits, two slits, and you have a screen over here. This is your capital D and this is your small d. Now these spherical wave, when they reach over here, it will form two wavefronts, and when they go, you have a dark band or a bright band. So what is happening over here? There is a alternate dark bands and bright bands due to the superposition of waves. Here one wave is behaving like a two different source because it is made to pass through the two slits or two small openings, and when the waves, whichever waves undergoes constructive interference will form a bright band, and whichever undergoes destructive interference, they will form a dark band. Remember, the thickness is same, and here the frequency is the necessary condition for interference is. So remember these points. The conditions for interference is the two waves should have almost same amplitude and almost same frequency, or you can say exactly same frequency or same amplitude or similar amplitudes. Same frequency is not possible using two sources, so we take one source and split it into two parts. Now using this, we have to find out one important thing, and that is called as the fringe width. So now we are finding out the fringe width, expression for fringe width. Now this is the slit, two slits, and this is the screen. This is capital D and this is small d. So this is the rays of light which is entering. Assume it is at the point P. They might be creating a constructive or destructive interference. It doesn't matter. Now I'll call this point as P, this as N, and these 2 points as AB. So now in the triangle, the first thing is the path difference is given by BP minus AP. What is the path difference? The extra distance traveled by the wave, and that is called as path difference. But that can be calculated using the two right angle triangles. So you will have it as, in the triangle APM, you will have it as AP square equals AM square plus MP square. So that is equal to capital D square plus, and if I assume from the center of the screen O, this distance is x, so you'll have it as x minus d by 2 the whole square. And from the triangle BPN, you will have it as BP square equals BN square plus NP square, which is equal to capital D square plus x plus d by 2 the whole square. So if you subtract these two, you will have it as BP square minus AP square equals, so d square will get cancelled, so you're left with x plus d by 2 the whole square minus of x minus d by 2 the whole square. This is of the form BP plus AP times BP minus AP, which is equal to 2xd. Now this is equal to 2d because if the point P is very close to O, the same distance, 2d into this is your delta, which is equal to 2xd. So from this you will have it as delta equals xd by d. So when you put the condition for the bright fringe, and for the bright fringe, what is the condition? Delta equals xd by capital D, which was the derived condition. For bright fringe, for a bright fringe, you will have it as xd by d is equal to, for the bright fringe, delta equals n lambda. So you'll have it as n lambda for nth fringe, or x equals n lambda capital D by small d for n plus 1th fringe. So for x plus nth 1th fringe, you will have it as n plus 1 times lambda d by d. If you subtract, you will get beta, which is equal to the fringe width, which is equal to lambda d by d. So this is the expression for fringe width, which you have to remember, students. So now with this, we are good to solve with the problems. So before we solve, okay, let us go to the first problem, which is on the screen. So you have the question, obtain the expression for resultant of two waves, which is given by the equation y1 equals 4 sine 200 pi t and y2 equals 300 sine 200 pi t plus pi by 2. So the resultant wave will be of the form y equals capital R sine omega t plus theta, where R is equal to root of a square plus b square plus 2ab cos phi, and theta equals tan inverse of b sin phi divided by a plus b cos phi. Here the value of small a is 4, b is 3, and phi equals pi by 2. On substituting, you will get r equals 5 and theta equals 0.2 pi radians. So the equation will be y equals 5 sine 200 pi t plus 0.2 pi. So 3 square plus 4 square forms a Pythagorean triplet. So the answer is 5 times, and you'll get the answer, the total value, as y equals 5 sine 200 pi t plus 0.2 pi. So now we have the next problem on the screen. Two waves have amplitudes in the ratios of 3:2. Find the ratio of the amplitudes and the intensity between the bright and the dark fringes. So this is a very nice problem, students. You can, first part you can take it, you can solve it very easily. You don't need much time for that. For second part, you just have to think a little for that. So it is not something which you don't know. You have already studied it. So I have just kept it so that you'll have a recap of your first year waves, which is very, very important. So here the ratios of the amplitudes is given by very simple a max by a minimum, which is equal to a plus b by a minus b, which is equal to 5:1. So this is the given data. So 5:1 is the answer for A. For B, the intensity is directly proportional to amplitude square. This you have learnt in your waves. So you'll have it as I max by I minimum is equal to a plus b the whole square by a minus b the whole square, which will be equal to 25:1. The answer for A is 5:1 and the answer for B is 25:1. So now we have the next problem on the screen. The maximum intensity of the two interfering waves is I naught. Find the intensity at the point where the phase difference between the two interference beams is pi by 3 and the path difference between them is lambda by 4. So you have to find the intensity at the given point. So here the given data is I max is equal to I naught. The shortcut for these formula is you can take it as I equals I max cos square phi by 2. So this is the formula which you have to use, students, for the point A. So I don't know what is the value of I. So I keep it as I is equal to I naught cos inverse, and the phi is equal to how much? Pi by 3, or phi by 2 will be cos inverse of cos square of pi by 6. Pi by 6 is 30 degrees, which is equal to root 3 by 2. And if you substitute this, you will have it as 3 by 4 I naught. And for B, you will have the answer as, we know that delta x equals lambda by 4, or phi equals to pi by lambda into delta x, or phi equals to pi by lambda into lambda by 4. Because they given it as lambda by 4, which gets cancelled, so the answer is pi by 2. So for phi by 2, or phi by 2 will be equal to pi by 4. From the previous problem, that will be equal to I naught by 2. So that is the answer for A and B, students. So now we have the next problem on the screen. So consider interference between two sources of intensities I and 4I. Obtain the intensities at the point where the phase difference is pi by 2 and pi. So we have the equation R is equal to root of a square plus b square plus 2ab cos phi, or this can be written as I1 square plus I2 square plus 2 times root of I1 I2 cos phi. So from this, for the formula, A will be equal to I equals, so under the root. So this is the I formula, so it is equal to I plus 4I. So this is I, not I square. So I1 plus I2 plus 2 times root of 4, and cos pi by 2 is 0. So this gets answer. So the answer has become 5I. And the next one will be I is equal to I resultant. So I resultant will be equal to I plus 4I plus 2 into 2, and cos phi is minus 1, which is equal to 5I minus 4I, which is equal to I. So this is the answer. So now we have the next problem. A monochromatic beam of light of intensity is incident on a glass plate as shown in the figure. Another identical glass plate is kept close to the first one and parallel to it. Each glass plate reflects 25% of the incident light on it and transmits the remaining. Find the ratio of the minimum and the maximum intensities in the interference formed between the two beams obtained after at each plate. So here the I1 value is equal to I by 4 and I2 value is equal to 9I by 64, and you'll have it as I max by I minima is equal to I1 plus I2 minus 2 times root of I1 I2 divided by so that is I minima, so this is plus, and I maxima, I minima is I1 plus I2 minus 2 times root of I1 and I2. If you solve it, you'll get it as I max by I minima is equal to 1 is to 49 is the required answer. So we have the previous class contest question. The blades of the rotating fan cannot be distinguished from each other due to the parallax, and the person to get the answer is Peru. Congratulations, Peru. You are the lucky winner of the contest question, with which you can clarify one doubt absolutely for free of cost. So now we have the today's contest question on the screen. Right, students, with this we have come to the summary of the today's class. We have dealt with the interference and the numerical problems. So thank you for joining us, students. I hope you have liked this video. If you have liked them, please do share this video among all your friends and help them also. And now it is class practice pack time. Students, we have given the 10 best questions from the topic which we have discussed today. It is available immediately for Passport members. For non-Passport members, you have to subscribe to Passport. Once you subscribe to Passport, you will also get access to 24/7 one-on-one dot solving and practice questions and the tests from the best-selling books and all the video classes covering interface concepts. I think you shouldn't miss this offer, students. So with this, I shall take a move from you all. But Passport members, don't go anywhere. Now it's CPP time. Good luck. All the best. Sayonara.